Okay, so welcome back everyone to this last session of the one word probability seminar for this term. It's my pleasure to introduce Eva Löcherbach and Elisa Marini, and they will talk, they will give a tandem talk on models for spiking neurons and jumps and stuff like that. So let me start introducing Eva. Which is from Paris 1 Panthéon Sorbonne University. And she will talk about probabilistic models for systems of interacting spiking neurons and some words about their mean field limits. So please, Eva, feel free to share your slides and to start this nice talk.
Good afternoon to everybody, or good morning, I don't know. So I'm Eva, this is Elisa. I will give the first talk and Elisa the second. We are on the same laptop, and so I will start right away. So, and I start sharing my screen, which should be now visible for everybody. Okay.
Yeah, great.
So it is. So I will speak about spiking neurons and their mean field models, and mostly about conditional propagation of chaos. And Elisa will also speak about conditional propagation of chaos in the second talk. And in my talk, I will give you an introduction to the subject to let you feel a little bit what this research direction is about. So I will give you a very short introduction to neurons and their biological functioning. I will give some ideas about classical mean field limits and the classical propagation of chaos property, and then spend more time on the conditional propagation of chaos. And this second part, which is the main part of the talk, is a joint work with Xavier Erny and Dasha Lukyanova, and Dasha Lukyanova is also on Zoom. She is from the University of Évry. So both of them are based almost in Paris. Okay, so I start with this introduction to neurons. So here you have a picture of one of them. So you see there is this long part of the neuron, which is the axon. That is actually an important part because the neurons, they generate and they propagate action potentials along of their axons. And these action potentials are actually transmembrane currents of ions, mostly potassium and sodium ions. This is a complicated procedure. I will not speak about that, but you should know that it is stimulated by ion pumps, and that all this happens due to neurotransmitters, which are the chemical substances at the chemical synapses. And in neurons, there is transmission of information from the presynaptic to the postsynaptic neurons, and this transmission goes by the action potentials. And more precisely, it is the postsynaptic neuron that listens to the incoming inputs from the presynaptic ones and accumulates, or people say integrates, all these influences in its membrane potential. And for the people in neuroscience, the unit of information is really the action potential. So the time at which there is this transmission of information. And this is why point process models make sense in this context. And this is what I will propose you in some minutes. Another reason for this point process models that they make sense is this picture here. Maybe you don't see it. It is a superposition of the spikes, or of these action potentials of a lot of neurons. And you see that actually, I mean, they all look the same. So it is really reasonable by just saying at this point here, there is the time of the spike, and this is the only thing I need to know. The picture was actually made by Reinhard Höpfer. He was my PhD supervisor, so a mathematician, and who got interested in these neuroscience things later in his life, and we also worked on that at some time. Okay. I think that's basically all I wanted to speak about. Yeah, well, here's a summary. So in the models that I will consider, neurons are reduced to points, which means that I don't take into account the fact that actually the action potentials are transported along of the axon. So it's a point. We only look at the action potentials at a fixed point. And then in all the models that we will see, we will be interested in the membrane potential process of the neuron. And I already said it, so this membrane potential accumulates the stimuli that come from the presynaptic neurons, and then the neuron spikes in a random way. So you can prove that it is random, depending on the height of the accumulated potential. And when the neuron spikes, it gives an additional amount of potential to its postsynaptic neurons, and this is the effect of the chemical synapses. And it is here that this transformation of information comes into play. Okay. So the models of this, they are called integrate and fire model. Integrate the summation of the input, and then fire, depending on the height of the potential, there is the action potential that takes place. And there are a lot of mathematicians that have worked on that. And on this slide, I just try to give you an idea what the people did. So there are people who worked more on diffusion models. I'm sorry, Laura, I didn't cite you here. So Laura Sacciadotto also worked on that. And here I basically cited the French community of people who looked on mean field models of interacting diffusions, where spiking is modeled when these diffusions hit a fixed threshold. This is not the kind of models that I will consider in my talk. My talk is, as I said, is devoted to point process models where we have stochastic intensity. So the underlying noise is Poisson noise, and the spiking times are generalized exponential waiting times with a weight that depends on the potential height. And I have been working a lot on this with Antonio Galvez. The first paper we did on mean field models of this was with Enrico Presutti, Anna De Masi, and Antonio. And then I made a follow-up paper with Nicolas Fournier. I worked on metastability in this context with Pierre Monmarché. We wrote recently a book on these kinds of models with Christophe Pouzat and Antonio Galvez, and I already cited Dasha and Xavier. And Elisa, sitting next to me, even though not visible anymore, also worked with us on this. I should also mention that a lot of other people worked on it. The Nice, or the southern France part of the French mathematicians, Etienne Tenré, Romain Welz, Quentin Cormier, Philippe Robert, who is from INRIA in Paris, Jonathan Tubul, Valentin Schmitz, and there is an important person from computational neuroscience, Wolfram Gerstner, who wrote several books about that. Okay. So I will now be more precise. So I will propose the model, speak about propagation of chaos, and then go to the conditional propagation of chaos. So in my model, we have n neurons. They are all described by their membrane potential values, which are the axes here. They are real valued random variables. And I already said we have stochastic intensity spiking models. That means that each neuron I spikes, so sends an action potential at a rate which is a deterministic function increasing of its membrane potential. And if it spikes, the neuron which is spiking itself goes back to zero. So the membrane potential goes back to zero. That is what you saw in the picture of Reinhard Höpfner. Zero is just by convenience, okay? We call this the resting value. And at the same time, the postsynaptic neurons of this neuron receive something additional, which is added to their membrane potential process, which I call W, I to J. So really we have something asymmetric here. It is the influence of neuron I on neuron J. And this W here is a fixed real number, which is the synaptic rate. Okay. So we have an associated structure of interaction graph. So two neurons have a directed link if I is presynaptic to J, which means that the associated synaptic rate is not equal to zero. Okay. So that was the spiking thing. And in between successive spikes, well, the membrane of a neuron is not something which is completely, when I'm looking for the English word, I mean, there's always some loss. Okay, so in between successive spikes of the system, we have loss of potential, and usually people from neuroscience, they take some linear drift like this, so we have an exponential loss in between the jumps. Other drift functions are of course possible, but that's not what people in neuroscience do. So this is the model. It is a piecewise deterministic Markov process. Okay, we have jumps the ones after the others. I didn't say much about this spiking rate function, this f of x. So usually we take something increasing from a neurophysiological point of view. It is reasonable to think that it is bounded because, I mean, the neuron cannot spike too much over time. We also have something like a refractory period. Okay. So I said we have n neurons, and actually n is very big, at least in human brains. It's 10 to the power 11. So it's really a lot of neurons. That means that if we stick to this microscopic description, we have a precise model with a lot of structure, but it is hard to compute something like invariant measures or whatever in an explicit way. And that is why people used to go to mean field models, that is to use mesoscopic descriptions, where instead of describing each single neuron, we just consider a class, a subclass of neurons which all behave in the same way, and then we describe them by their empirical measure. And of course, that is only possible at some scales where the synaptic weights, so they depend on n, the number of neurons in the system, tend to 0 at some weight, such that we get something which is not degenerate in the limit. Okay. So I take mean field interactions, as I said. So I have subsystems of the brain where the neurons all behave in the same way. And I suppose that the synaptic weight from neuron I to neuron J doesn't depend on the pair of neurons that is involved. In other words, the underlying graph is complete. Okay. So in some subsets of the brain, this makes sense. And then we will describe the neurons rather by their empirical measures. And this mu n is always the same notation throughout the two talks, I guess. So mu n will be the empirical measure of the neurons. And it is an empirical measure on the trajectories. So on the whole path of cut-lug trajectories of the membrane potential processes. Or we will also consider the projection on a fixed time, and then it's the empirical measure of the state of the system at a given time t. And then if we are able to find something to prove that there is a limit of this sequence of empirical measures, and this limit will always be called mu, then with some hope, this limit measure is something easier than the big system, and we will rather describe the system by this limit here than by the finite mu n. Okay. And so this limit measure mu is in the center of the two talks of today. Point. Okay. And we will propose you two approaches. I mean, most of you, those who know propagation of chaos, you probably know this. So there is the strong approach, which goes as follows. I guess somehow the limit. So I let formally n tend to infinity, and then I try to understand what is the limit, and then I prove convergence to it by coupling. So that is what we would call the strong propagation of chaos property. And this has the advantage to give us also a speed of convergence. But of course, we need more. We just prove the convergence to the limit by compactness, tightness arguments, and get the uniqueness from some Martingale problem and the uniqueness of this Martingale problems. And this is what I'm going to talk about in the second part of the talk, because we think that we have found a very nice Martingale problem in this context. Okay, so I start right away with the classical situation, which is the situation of propagation of chaos. Okay, so this means that I'm in the scaling of the law of large numbers. I suppose that I have, so I remember n neurons, they all have the same decay rate, they all have the same spiking rate function, the way they react to incoming stimulus, and the synaptic weights are something fixed divided by n. So the scaling of the law of large numbers. Then I can rewrite the evolution of each membrane potential process in this way. So I have the exponential loss. I will not speak about that anymore in the sequel. And then I have the red and the blue term. The blue term is the reset to 0 each time that neuron I spikes. So capital Z is the spike counting process of the ith neuron within the system of n neurons. Okay. So it's the counting process, which is +1 at each time I have a spike. And this is the synaptic integration part. So this is the incoming spikes of the other neurons that gives something additional to the membrane potential of neuron I. So it's W divided by N, the membrane the synaptic weight. Each time that another neuron spikes, I get this additional amount of potential. And it is convenient to represent all these counting processes which have a stochastic intensity by means of an underlying two-dimensional Poisson random measure, which has intensity Löcherbach in time and Löcherbach in space. This is just a convenient way of simulating, if you want, a point process which has an intensity that depends, that is random and depends on its position. Okay, so you can think of the Z variable here as an acceptance rejection variable that allows me to accept the proposal jumps of the Poisson random measure according to this procedure. It's something classical in jump processes. Okay, and of course I take the underlying Poisson random measures for all the neurons independent. So I have independent Poisson noises for all the neurons. They interact only through the jumps. Okay. So since Luisa is one of the two organizers, I wanted here to cite her in, I think it was her thesis. So Luisa, Paolo, and Marcus called the red term the collateral jumps, okay? Which means that each time I have a jump which is generated by pi I, by the neuron I, it gives rise to the big jump, the reset to zero of the neuron itself, and then we have the collateral jump, the synaptic integration, that adds something additional to the others. Okay, and the blue term is the term of the big jumps, which is due to the reset of the spiking neuron. I just checked the time. Good. So now I want to let n tend to infinity and to understand what is the limit behavior of that. And I thought that the most convenient way of convincing you, if you never saw this, is to do the following. So I take my spiking counting process of a fixed neuron, and I just center it. Centering means that I subtract the integrated intensity. This gives me a martingale. If you don't like this way of writing, you look on the left-hand side here. I have the integral against the Poisson random measure, which is compensated. Okay. Anyhow, so it is a pure jump martingale. And if I compensate the jumps, I can rewrite my collateral jumps in this way. It is a sum of martingales. The martingales are all supported, I mean, the underlying Poisson random measures are independent. And then I get, from the compensation term here, I get an additional drift, which is actually the mean total spiking rate of the system. Okay, so up to the fluctuations, because this term here is of order 1 over square root of n, I already get something which where the mean spiking rate of the system is a drift. And so it is rather natural to think that in the limit, well, the fluctuations disappear, and this drift here, which is an empirical mean, will converge to the theoretical one, like in the usual law of large numbers. And this is really what happens. So if I choose the initial conditions for the membrane potentials at time 0 as I should, then I have weak convergence of the empirical measures to a limit one. And the limit mu is the law of any of the fixed neurons in an infinite IID system of neurons, and where each neuron follows this equation. So I still have the exponential leakage, I still have the big jumps due to the spiking, and the interaction with the other neurons has become a drift, which is given by the mean spiking rate, the theoretical one, so the expected spiking activity of any neuron at that fixed time. Okay. So this is true under certain conditions on the function f. I don't want to discuss that now. I just wanted to tell you that you have to think a little bit about that. We did it for functions f, which are like power functions, such that we could say x divided by some threshold to the power p for large p, such that this means that, well, at the threshold, you're really very likely to spike. Okay, so there is some work to be done, but I will rather speak about that in the second part of the talk. Okay, so, and this is called propagation of chaos, because in the limit, the membrane potentials are all independent. And so it is a sort of dynamical version of the law of large numbers, because if initially the configuration of neurons is chaotic, which means IID say, then this chaoticity is propagated over time. And then maybe last word already about the strong propagation of chaos approach. It is possible here to couple the finite neuron system with the limit system by using the same underlying Poisson random measures. This is what people call the simultaneous coupling. And then we have actually a rate of convergence for the Wasserstein run distance of the membrane potential, which is at least on fixed time intervals of orders 1 over square root of n. And this has been done by several people, for example, also Philippe Robert and Jonathan Tubal. And then the question is if we can extend that to longer time periods or not. And maybe I come back to these questions on the long time behavior of the limit systems at the end of the talk, if the time is still there. Okay, so that was the first part of the talk. I will have some water because it is hot in Paris. And I go to the second one. Shouldn't be written propagation of chaos, but conditional propagation of chaos. So this is now the main part that I wanted to tell you. So it is about systems where I still have mean field systems of neurons, the same model, except that now I suppose that the synaptic weights, these W's, are random and that they are actually centered and then renormalized by square root of n such that I'm in the, well, if you want, in the domain of attraction of a Gaussian law. Okay, the fact that the U's are centered, that relates to the fact that we want to consider balanced networks. There are some biological motivations for that. So somehow we restrict attention to networks where the excitatory and inhibitory inputs are balanced. Okay, and I should say that we have independent choices of these U's at each spiking time. So I will be more precise now immediately, so you see it here. So I write again the evolution of the membrane potential of each neuron. I have the big jumps here, but now I have underlying Poisson random measures which have 3 dimensions. So I have time, I have the acceptance rejection variable for the random spiking weight, and then I have an additional variable u, which is the random height of the synaptic weight that is chosen at each spiking time. Okay, so these pi's now have an intensity nu du in the third variable, which gives you the choice of the random heights at each jumping time. And this nu is supposed to be centered. Let's say we take a variance 1, so we have at least a moment of order 2. Okay, that's all. So, and then if we want to go to the limit, as before, of course, the interactions do only appear at the moments of the jumps due to the spiking. So we have to understand what is the limit of this term here, the second one, the term of the collateral jumps. So it is written here once again. Now it is the martingale itself. We don't need to center it because the U's are already centered. So the term of collateral jumps is the martingale. You see that is renormalized as it should. So it is of order 1. So we have a lot of jumps. We have n times f intensity jumps, but the jumps are of height 1 over square root of n. So we imagine that in the limit, it will converge to something continuous. And to understand what this continuous limit martingale will be, we just calculate the quadratic variation of it. So this is what I did here. Since I took the U's to be of variance 1, if you take the square of that and the expectation, well, that gives you just the integrated mean intensity once more of the system. So the intensity, the integrated intensity is now linked to the variance of the collateral jumps. And if we suppose that that we have convergence of the empirical measures, then the limit variance should be, well, the integrated intensity of the jumps in expectation. So this is why we think that the limit martingale should be something continuous. I said because the jumps disappear in the limit. So I have the integral from 0 to t of the square root of the limit spiking intensity integrated against the Brownian motion. And the Brownian motion was not present before in the finite system. it pops up because we have the central limit theorem, which gives rise to it. Okay. So we have a limit system, still an infinite number of neurons. It should be at least an exchangeable system. It is given by this equation, and you see that we have we have underlying Poisson random measures which account only for the spiking activity of each neuron. They are all independent. But then there is this additional Brownian motion, the B here, which is common to all of the neurons because of the synaptic integration part. So we have some common source of noise, and of course, then the neurons are not independent anymore. They are conditionally independent, conditionally on this common noise. And this is called conditional propagation of chaos. Okay. And as a consequence, actually, the limit empirical measure, so the limit of the mu n's, will not be a deterministic measure anymore. Before I told you that mu was the law of any of the particles in the limit. Now it will be a random measure because it will actually be the directing measure of the limit exchangeable system. Okay. So if you don't know what are directing measures, here is a short summary of the classical theorem of Definetti, Hewitt, Savage. So in this case, so if we have an exchangeable, infinite exchangeable system, then the joint law of all the particles is a mixture of IIDs, which means that conditionally on the knowledge of the directing measure, the mu t here, remember mu t was the projection onto time t, well, all the particles are IID copies of this random measure. So I first choose a random measure, and then conditionally on this random measure, I choose IID copies of it. So it's a mixture of IIDs. Okay. And it turns out in our system, because B, this Brownian motion, is the only source of common noise, at least if initially I take all random potentials to be IID, that the limit, that the directing measure has to be the conditional law of each of the neuron potentials giving the common noise, so given B. And so to finish this first part of the second part of the talk, I'm actually guessing the limit. That's what I'm doing here is, so the limit equation should be given by this one. So I have the jumping part, the spiking part, exponential leakage, and the synaptic integration, which is a Brownian diffusion part, and where the volatility is the square root of the conditional expectation of the spiking rate of any of the neurons given the common noise. Okay, and in what follows, I will just use the last 15 minutes to tell you how we prove the convergence and also how we prove the well-posedness of this limit system. Okay. So why could there be a problem with the well-posedness here? Well, there are several reasons for that. So first of all is we have conditional expectation here and the square root term. This is why we will need to assume that f is actually lower bounded, such that we can handle this square root here, okay? And then there is another problem which we already had in the classical propagation of chaos part. It is these big jumps to zero of the spiking particle, because even if the spiking rate f is Lipschitz, you have x times f of x here. And this is not necessarily Lipschitz anymore. So it is difficult actually to handle this reset to zero of the spiking neuron, because imagine you have two neurons which are very close in potential, and the one is spiking but not the others. After the spike, the one who spiked is back to zero, and the one which is upstairs is still there. Well, that was not a good explanation, but you should trust me that these big jumps are causing problems. And then there is a last problem where we have this jumping part here with an indicator function. We accept or not jumps, so there's this indicator appearing. So usually one has to treat these terms in an L1 distance, okay? And then we have the Brownian part, which is usually tackled in L2 distance, of course, because we have E2 isometry. So there's this question, should it be L1 or L2? Elisa will maybe also speak about some of these problems that we don't have the right norms in the finite particle system and in the limit one, that they don't match. So we have to find some compromise in between them. Okay. So here's the theorem, and then I explain it. So the theorem with Xavier and Dasha was, I have to impose something. Okay, first of all, f, the spiking rate, has to be lower bounded, such that the square root term doesn't make any problem. And then I need some control on the decay of its derivative. Basically, that means that f is bounded, and you see it as f prime, the derivative is fastly decreasing. In this case, I have trajectorial uniqueness of this limit equation, and we can construct by pk iteration a unique strong solution of it. And the proof of this is a very nice proof. It is an idea that I learned from Nicolas Fournier really long time ago. The idea is to handle with these big jumps which have non-Lipschitz terms, instead of considering, so say I have two solution processes which are driven by the same noise, and I want to prove that they are the same. Instead of saying I consider x minus y in L1 or L2 norm, I put them in a space transform, and I rather consider a of x and a of y, and I try to compare that. If this space transform, I call it a distance function here, is sufficiently big, good, I called it a Gronwall function in my slides. That means it is a function that is really made for my dynamics, such that if I apply Ito's formula to it, it behaves as it should if you want Gronwall to work. Okay, this is written here. I'm not commenting it, but that is the way we deal with the big jumps. And actually, under this condition, it is basically possible to take A equal to F to the spiking rate function. Okay, so if F would be a if it is bijection, then I can just take f of x minus f of y as a distance. And the moral behind this is that, well, we have to compare the spiking rates of the two systems to decide if they are close or not. Okay. And then there is this very nice, even older idea of Carl Graham, who said that, okay, now that I have understood that I have to first apply this space transform, then to cope with this L1, L2 problem, you should rather take an L1 norm, but uniformly on finite time intervals. Okay, and then you use Brockheuser-Davies-Grundy inequalities to deal with the Brownian term. So actually it works on each finite time interval, and then we are able to prove that for this kind of distance, we get a contraction on small time intervals that gives us the uniqueness, and then I use the same ideas to prove existence by pk iteration. Okay. So this was some words about the well-posedness of the limit equation of this one. And so I know now that the limit equation exists. Now you could, I have a strong solution of it. I didn't prove that I converge to it. I just proved that the limit system exists somewhere. Okay. And I will not prove now the convergence by coupling. I will just prove it by the Martingale problem approach, so the weak approach. And this is what I'm going to tell you now. So it's the second main theorem of the talk. So if initially I take IID configurations for the membrane potentials, some moment conditions, then I have weak convergence to the limit law, which is the conditional law of any of the particles given the common noise. And the proof is by tightness. That is easy. So we know we have converging subsequences, and I just need to identify any of these limits. And I do this by a new Martingale problem, and this I wanted to spend some time on it. Okay. So we know already that in the limit system, the nuance, they will be dependent because we have correlations there, because it's an exchangeable system. It's not IID anymore. So somehow we need to express the correlations in the Martingale problem. The way people usually do, I mean, there are a lot of people working with common noise. Usually they just add the common noise to their dynamic, such that they have something two-dimensional, say, and in this way they account for the correlations, if you want. We can't do that because the Brownian motion is not present at the level of the finite nuance system. It would just be independent of anything, okay? So we can't just add the Brownian motion, and so we did something else. So instead of that, we worked with couples of trajectories, not only single ones, but couples and laws of such couples. Okay, so here comes maybe rather not very digest a slide. I try to be pedagogical. So I said I work with couples of trajectories. So each trajectory will be a Cadillac trajectory. So an element of the space of the Skorokhod space. And I'm interested in probability measures on these trajectories. That is my limit object, the measure mu, the random measure mu, which is a probability on Cadillac trajectories. Okay, so I'm interested in this mu here. And I suppose that I have one of these limit mu's, so I have the law of it. Okay, good. And then I will work on the canonical space, which is this one. It is couples of random measures and couples of trajectories. Okay, so if you want, it's triplets. So my random objects will be random measures and capital Y's, which are two copies of two neurons in the limit. Okay. And I construct, starting from the law of any of my limits of the empirical measures. So from my mu, I will construct a new measure P on this space P times D2 by just mimicking what it means to be an exchangeable system directed by mu. So saying it differently, I have this limit object mu. I construct an exchangeable system directed by it, and then I just take two of the coordinates, and I take the joint law of mu and the two of the coordinates, and this gives me the P. It's written here. Okay, so this just tells you that conditionally on the random measure, the two trajectories are independent and have the law, which is the random measure. Okay. So, okay, so this is somehow natural. You have a limit object, which is a random measure. You take it as a directing measure, and that gives you something more. You construct, you are interested in the joint law of the two coordinates and the limit measure. Good. And then I say that Q, so the law of my directing measure, is a solution to the Martingale problem if for all good test functions on two particles, G of yt, so remember y is two particles minus G of y0 minus the generator is a Martingale. And the generator is the one that you imagined. That is the one that you would get from Ito's formula. So we have the exponential decay. We have the jump terms. We see that the two particles are supposed not to jump at the same time, so they will be driven by independent Poisson noises. And then we have the common volatility, which is given by this mu of f. And mu is random. It is part of the randomness. Okay? Good. So this is a classical Martingale problem. The only thing is that we added the randomness in the mu. And that I look on couples of trajectories, and I will explain why it is couples in 2 seconds. Okay. Then the rest of the proof is classical. So first of all, you prove that any possible limit of any convergent subsequence of our empirical measures solves the Martingale problem. This is easy. You just use Taylor. I mean, it's technical, but easy. And then I have a representation property for the canonical process, the two trajectories under this measure P on this bigger space where I have random measure and two trajectories. And it tells you the following: if I have any solution of the Martingale problem, then the canonical process, the trajectories of it, they solve the right stochastic differential equation. This differential equation is driven by two independent Poisson random measures and a single common Brownian motion. And I have the right volatility, of course, because it's the one which is given by the Martingale problem here. Okay. The only missing point here is that I don't know what is the structure of mu for the moment. I don't know yet that mu is conditional expectation given B. I will come.
Eva, can I just stop you 1 second? If you go back to your previous slides, you have mu, but then this mu, it's measured on a full trajectory or at a given time?
It should be mu
S. Okay.
It should be mu s here. So
it's a projection at a given time.
Yeah, because here it's mu s. So it is.
I see. Yeah.
Of course.
Yeah. Thank you. Yeah.
Misprint. Yeah. Okay. Okay, so I was here. So this is also not that difficult. You use classical results that you find in the book of Ikeda Watanabe, things like this. Okay. And now I try to explain you how I finished the proof. So now comes the theorem, and so we accept these two lemmas, and here comes the theorem. So each measure mu that solves the Martingale problem is necessarily given by the conditional expectation of the strong solution of the limit system that I constructed given B. And in particular, we have uniqueness, and we know that each converging subsequences converges to that, and that gives you the convergence. Okay. And just 2 words on the proof. So I take my mu and I construct an infinite exchangeable system which is directed by mu. I call that y bar I. It's an infinite number of particles. Now I take any 2 particles of this infinite system and I look on the joint law of mu and these 2 particles. It's this measure P that I constructed some slides before. Okay. And I will do anything for these triplet mu, yi, yj in the sequence. So I use the representation theorem. So I know that yi and yj solve the right stochastic differential equation, and that this is driven by 3 noises, which are independent: a Brownian motion, the first Poisson random measure, and the second one. And maybe the Brownian motion depends on the couple of particles because it's common to yi and yj, but I don't know that it is not depending on ij. But then I use exchangeability, so I can apply the same argument for any other couple of particles. So say ij and ik. And by uniqueness, I deduce that the driving Brownian motions have to be the same. And this allows me to actually understand that there is only one single Brownian motion that is underlying all the particles. Okay. Good. And this is the end of the proof. So I have the right stochastic differential equation, and I know that mu of f in this limit is the conditional expectation of any of the spiking intensities given the common noise, which means given mu of y. But I want to know that it is actually the conditional expectation given b. And to identify this, I think I don't have very much time left. I use an interpolating 5 minutes, you think? Yeah, let's say 3 minutes. I use something which is usually done in these kinds of problems. I use an auxiliary particle system, which is a mean field version of the limit system, and that allows me to interpolate in between these 2 systems. The strong system that I already constructed in the beginning, and the weak system, say the y's, to which I converge what I just proved, and this way I'm able to prove that the 2 are actually the same. Okay, and that is the end of the proof. And so I have some minutes left. So I just wanted to tell you that, well, actually we also got a strong rate of convergence in another paper, still with Xavier and Dasha, where we have coupled the collateral jumps with the time-changed limit Brownian motion. And this was done by using the coupling, the famous one by Komlosh, Major, Tushnadi, which you can also see in the works of Tom Kurtz. And Elisa will speak more about such ideas in the second talk. Okay, and so up to now, I just proposed 2 things. So I discussed the large n limits of systems of interacting neurons with the synaptic weights in 2 cases. So the first one was the classical propagation of chaos setting where Wn was of order 1 over n. We had a classical Makin-Vlasov limit equation that depends on an additional drift, which is the expectation of the spiking intensity dt. And then I had the second part of the talk where I discussed the diffusive setting and where the synaptic weights are random and centered and in the domain of attraction of a Gaussian law. And then the limit is conditional Makin-Vlasov, if you want to call it this way. And where additional to the jump terms, you have a diffusion term that appears, which is given by this. I prepared some comments on the large time behavior of the limit system, but I think I will skip it. If you want to have a look, it is on the slides which are on the internet, and so I just skip them. And I finish with some literature. So I wanted to cite the paper by Luisa. And this one is the first one we did on the propagation of chaos with Antonio, Anna, and Ilko some time ago. Then the paper with Xavier and Dasha. And the one with Nicolas and with Karl Graham, which is a nice paper from 1992 on McKean-Vlasov Ito-Skorokhod equations in general. Thank you for your attention.
Thank you very much. Thank you very much, Eva, for this very nice talk. And so let's see if someone has questions. Please just unmute yourself or write in the chat, whatever you prefer. So maybe I start with one question. And usually when you think of this McKean-Vlasov type of SDE, so nonlinear SDE, the law of the solution of such an SDE is the solution of a nonlinear PDE. So this means that I can think of your mu as the solution of a nonlinear SPDE?
Yes. Yes.
Okay. So
exactly.
where the noise, it's somehow also, because if I've understood correctly, the hard part of this common noise is also that the coefficient, the diffusion coefficient, depends on the law itself, right?
Mm-hmm. Exactly. So in the SP, but I'm not an expert. At some point I had these slides, but then I threw it away because I don't know anything about SPDEs, even if I should. But you can imagine that in the SPDE, because it is a PDE about the conditional laws, how the Brownian motion is still present there.
Yeah.
This B here, yeah.
Ah, yes. Yeah. And you mentioned that, I think probably I just lost this. So you mentioned that in order for this not to create problems, you want F, so the square root, you want F to be lower bounded. Can you give a rough idea of why?
Well, if you want to compare, so say I want to prove uniqueness of the limit equation. And I have a process X and a process X tilde, which both of them have a volatility term of this type. And you want to compare them. If you want to do that by using the Lipschitz property of F, you have to be able to compare the square root of this expectation to the square root of the other expectation. If F is lower bounded, then this is still Lipschitz. So basically what I'm telling you that the application that mu goes to, sorry, I'm not, I don't have a whiteboard, but that this application here still is Lipschitz, actually. So this is, okay, you might say that we are cheating, but at least from the neuron perspective, it's not that much cheating, because to have some minimal spiking activity is very much okay.
Okay, yeah, makes sense. Yeah. So I see that there's something in the chat. So let's see if the person wants to unmute themselves, or I can read the question.
Okay, thank you. I can unmute myself.
Thank you.
I wasn't sure what to do. Okay, thank you very much for the nice talk. I had a question. I don't know how naive it is, but I would like to have some heuristics on choosing the distance function A in the well-postness proof. So thank you very much again.
You are speaking, yeah. Yeah.
Yes, exactly. Like some heuristics of how to choose it. What will be the goals when you are looking for this function?
Look, so same answer as the one to Elisa. So suppose I want to prove uniqueness, trajectorial one of these equations. So I take one equation with X and the other one with Y. I use them with the same underlying Poisson noise, and I want to show that if they are close, that they remain close by the dynamic. Okay, and if I suppose that F is Lipschitz, what is dangerous in this spiking activity is here, even if you have two close particles, it might be that the one of the two is spiking, but not the others. And that means that you have a jump which is of order X. And the difference of the two spiking activities, is X times f of X minus Y times f of Y. and this is not behaving well. If I use this transform, actually, if I use this transform here, as I told you, actually, the transform that I'm using is basically the spiking rate function itself, and it turns out that this transform is very well adapted to these big jumps. This is not a good explanation.
Yes,
I can
thank
send
you.
you an email after. So it is
Thank
really
you.
to cope with these big jumps, actually.
Thank you so much. Yes, very nice talk. Thank you.
Thank you. That's very kind of you.
Thank you very much. Are there other questions?
Will you speak about a function? No, actually not. Yeah. No.
Okay, so can you give us at least a hint of what you were saying about the long time behavior that you said it's already on the slides? The slides are online, but maybe you can quickly drive us through that.
Yeah, I mean, thank you. Thank you, Luisa, for this. So of course, once you have proven the convergence to the limit, the question is, now I have the limit, maybe I'm interested in its limit, in its long time behavior. Does that say anything about the finite system? And I worked a little bit on that in the classical propagation of chaos setting, for example, in the framework of Hawkes processes. So I'm a little bit quick here. The framework of Hawkes process is the same model, but you throw away the big jumps. So you just say, okay, there's spiking activity. At each activity, I give something to the presynaptic neurons, but the membrane potential of the spiking neuron stays where it is, okay? So this is what people call nonlinear interacting Hawkes processes. And in this framework, the limit process is very easy because its membrane potential solves a deterministic ordinary differential equation, this one. So we just have dxt is exponential leakage plus wf of xt. And then, of course, you can solve this for stationary points. I mean, any stationary solution of this would be a Poisson process having a rate f of x star, where x star is solution of this equation. Good. You can prove that if we are looking on isolated systems, here I should cite Alini Duarte, who is also on Zoom. So if we have a spiking rate which is 0 and 0, so here is not lower bounded, okay? We forget about that for a second. Then, of course, the 0 spiking activity is always a stationary state, and we would then speak of extinction of the spiking activity. But one can prove that for sufficiently good functions f, if they are concave and large synaptic weights, we have a phase transition, and we have a second equilibrium for the limit system, which is related to sustained spiking activity. And we can reformulate that as metastability for the finite neuron system. So which remains active during a very long time and then suddenly becomes inactive because, well, the only invariant measure of the finite system is actually the silent measure. Okay. So we did some work with this also in, this is some citation of work with Susanne Dietlefsen, where we had processes in several populations, and we were able to study the impact of delay in the spiking transmission. And we proved that that gave rise to oscillations in the limit intensities. And these oscillations have actually been proven also by Quentin Cormier, the guy from southern France, for the true model with reset by functional analytic methods. And as I said, this metastability, we studied it in the model with reset to 0, so not the Hawkes one, but the one I was speaking about with Pierre Monmarchais. Yeah. So this is but this is all in propagation of chaos setting. To be honest, we did not even start to think about the long time behavior in the case of the diffusive scaling because it's not that evident.
Mm-hmm.
It's much more complicated.
You still, do you still expect that there is some sort of stationary measure then? Because then
it could, yes, of course.
It should,
But then, I mean, I then have a process. You need the stationary T of this conditional expectation process. Okay.
Yeah.
That makes perfectly sense, but it's not something that I have studied for the moment.
Yeah, makes sense. Yeah. Okay. Yeah. Oh, thank you very much. Yes, that's that's a nice. Yeah. Okay, so let's see if there is some other question, and if not, I propose maybe that we take something like 5 minutes break. So, okay, so it's a pleasure to introduce Elisa Marini as the second speaker of today. And Elisa is based in Paris at CEREMAD, Université Paris-Dauphine. And she will talk about strong conditional propagation of chaos for systems of interacting particles with nearly stable jumps. And so please, Lisa, the floor is yours.
Okay, so thank you very much to everybody for being here. And thank you to the organizers for the opportunity to give this talk. And as Elisa has told you, I will speak about this strong conditional propagation of chaos for systems of interacting particles with nearly stable jumps. So this is a joint work with Eva, which was already spoke, and with Dasha, who is online today. And the very general setting of this talk, of this work, is the large volume behavior of systems, of a class of systems of interacting particles. So I won't speak about long time behavior, I will just speak about a large volume behavior. And in particular, I will show you that this class of systems that we consider in our work have a sort of the conditional propagation of chaos property. And so just a quick reminder for those of you who are not there before, or just Eva already explained that when we say that a system of interacting particles has the propagation of chaos property, what we mean is that whenever we initialize the particles of the system with independent and identically distributed initial conditions, roughly speaking, then despite the fact that particles in the finite system are interacting, when I consider the large volume behavior of the system, so when I send the number of particles to infinity, then I find that particles behave independently and they are identically distributed. And in the case of conditional propagation of chaos, which is the case in this work, the case that I will speak about, this means that when I initialize a particle of a system with independent and identically distributed initial conditions, then in the limit, when the number of particles diverges, they are not independent, but they are conditionally independent, conditioned to some source of common noise in their dynamics, to some stochastic process which is common to their dynamics. Okay, so this was just a quick reminder. And before presenting the class of systems that we considered in our work, I then need to explain you what I mean by nearly stable jumps, so the second part of the title. And to do this, I need to recall some basic facts about alpha stable random variables and random variables in their domain of attraction. No. Sorry.
No, it should work.
Should work? Oh, yes. Okay, sorry. So we will be interested in particular in strictly alpha stable random variables. So we say that the random variable x is a strictly stable random variable with a stability index alpha between 0 and 2. If calling xi independent and identically distributed copies of x, for any finite sum that we take of these IID copies of x with a proper rescaling, then we obtain that this new random variable is equal in distribution to x itself. And then we say that a random variable u belongs to the normal domain of attraction of a strictly alpha stable random variable with some stability index alpha, if the so-called stable central limit theorem holds, which means if for any finite sum of IID copies ui of u that I consider with a proper centering and a proper rescaling, then I get a quantity that converges in distribution to the strictly alpha stable random variable x. Okay, so in particular, in this, keep in mind this stable central limit theorem, because we will need a conditional version of it in the rest of the paper. And just a remark about this stable central limit theorem. So these constants a with n can be taken to be equal to 0 either when the limit random variable has a finite first moment equal to 0, so it's centered, or when the limit random variable does not have a finite first moment. And when I say a proper rescaling, what I mean is I take power 1 over alpha of the number of random variables that I'm considering in this sum. Okay, and for instance, an example of this, you can take for a stability index alpha equal to 2, you can consider a centered Gaussian random variable that is a strictly alpha stable random variable with alpha equal to 2. And its domain, normal domain of attraction, is made up of all those random variables that have a finite second moment. Okay, and speaking about moments, the peculiarity of strictly alpha stable random variables for alpha strictly less than 2 and of variables in their domain of attraction is that they have finite moments of order q only for q strictly less than the stability index alpha. So they have heavy-tailed distributions. They can assume with non-negligible probability very large values. And so in the rest of the talk, when we speak about nearly stable jumps or nearly stable random variables or nearly stable law, what I will mean is basically I will consider laws in the normal domain of attraction of some strictly alpha stable law. And actually, in our paper, we take some extra assumptions when we speak about the nearly stable jumps, but I won't speak about these assumptions now. So just imagine that nearly stable jumps means jumps in the normal domain of attraction of a strictly alpha stable distribution. Okay, and for the rest of the talk, then we will fix a stability index alpha strictly between 0 and 2 and exclude the case alpha equal to 1. And we will denote by nu the law of a nearly stable random variable, so the law in the domain of attraction of a strictly alpha stable law, in the case alpha less than 1. And in the case alpha greater than 1, we will consider some law in the domain of attraction of a strictly stable law. We will center this law, and we will call nu this centered version of the law. Okay, so in the case alpha greater than 1, we are speaking about centered random variables. Okay. Now I can finally present our finite particle system. So as in the case that I have spoke about, we consider n particles that are described by their positions x and I that are real valued positions. And all the particles will behave like piecewise deterministic Markov processes. So this means that all they can do is they can follow deterministic vector fields and they can have random jumps. And these are the equations satisfied by the particles of our finite system. So we have what I will call a drift term, what I will call a main jump term, and what I will call, again, citing Luisa, a collateral jump term. And so this tells you that any particle I in our finite system can, in between a successive jump, can follow follows a deterministic vector field with a drift B, which is a function of the particle position and of this mu and s, which is, again, have I introduced this object before, but I will repeat it. It's the projection at time s of the empirical measure of the system, so an average of direct delta functions in the particle's position. And the two important assumptions that we make on this function b is that b will be bounded and Lipschitz continuous. In particular, Lipschitz continuous with respect to some convenient Wasserstein distance on the space of probability measures on R, which is the space where this random measure takes values. And then we need to describe the part of the dynamics that involve random jumps. And so to this aim, again, these are objects that I've introduced before. We consider a family of independent Poisson random measures on R plus times R plus times R, this pi I, with an intensity that in particular contains this nearly stable law nu. And we will also consider their projected versions. So we integrate out last coordinate, and I will call the projected versions bar pi I. And these will be, again, independent Poisson random measures, this time on R plus times R plus, with a Lebesgue intensity. And so now I can tell you this is the main jump term. What does this mean? This means that every particle, for instance, particle I in the system, can jump with a rate that depends on its position via this function f. So rate function as the rate functions that I've considered before. That depends on the particle position, particle I position before the jump, and which will be which we assume to be bounded, lower bounded, and Lipschitz continuous. And whenever this happens, we say that particle I performs a main jump, and its position is changed by the value taken by this function psi, which again is a function of the particle position before the jump and of the empirical measure of the system just before the jump. And as in the case of B, we will take in particular the psi to be bounded and the Lipschitz continuous, again with respect to some convenient Wasserstein distance on the space of probability measures on R. And in the case alpha greater than 1, we will also assume for some technical reasons that this psi will be identically equal to 0. Okay, and then last we have this term, the collateral jump term, and this is telling you that any particle I in the system does not only jump when the Poisson random measure pi I associated to particle I as an atom, but it can only change its position when any other particle j different from I in the system has a main jump. That happens according to the Poisson random measure of particle j and with a rate that depends on the position of particle j. And when this happens, we say that particle I performs a collateral jump. So its position is changed by this quantity, which is given by a random variable u, in a nearly stable random variable u, so distributed as the law nu, and scaled by the size of the system to the power 1 over alpha. And this term is also telling you that whenever some particle in the system has a main jump, then all the other particles in the system receive at the same time the same random amount, which is given by this quantity, and it is resampled independently anytime. So overall, when a particle I in the system has a main jump, two things happen. Its position is changed by psi, and the positions of all the other particles are changed by some random variable, nearly stable random variable u, divided by n power 1 over alpha. And as Eva explained better than I will do, these kind of systems can be employed to model families of interacting neurons. So in particular, in this setting, these positions represent the membrane potentials of the neurons. And you can think that main jumps represent the moment when a neuron has a spike, so it sends an action potential to other neurons. And the collateral jumps in this setting would represent the synaptic inputs that postsynaptic neurons receive from presynaptic ones. Okay, and for this system, we can prove a strong resistance and uniqueness, so everything is well posed, and we can really start thinking about which is the limit of this system when the number of particles diverges, and in which sense we have a limit. So if everything is clear for the finite dynamics, I will go to the limit system, and I will present you the limit system before stating the main result of our work. So the limit system is an infinite exchangeable system, which means, again, it is invariant under any finite in distribution, under any finite permutation of its components. And again, we have a drift term, a main jump term, and a new term. Here you see that in the coefficients of this system, in place of the empirical measure of the finite system that we had before, we have this mu bar S, which is the conditional law of any of the coordinates of this infinite exchangeable system conditioned to this process S alpha, which I will introduce in a moment. And this mu f, which appears here, is standard notation to denote the average of a function f with respect to a measure mu. And then again here, we have again these bar pi I, which are again independent Poisson random measures with Lebesgue intensity as were before the projected post-random measures in the finite system. Again, psi is identically equal to 0 when alpha is greater than 1. And finally, this S alpha appearing here, which was not there in the finite particle system, is a strictly alpha stable process. So in particular, it is a Levy process with strictly alpha stable distributed increments. And it is independent of these bar pi I, these post-random measures. And so maybe it is a good moment now that we have this limit system here to make some comments about this S alpha. So as you see, this S alpha does not depend on the coordinate I. So it is the same random process which is present in the stochastic differential equations of all the particles in the limit system. So this is what we keep calling in this talk a source of common noise. It is present in the dynamics of all the particles. It can, for instance, it can jump. It's a Levy process, and when it jumps, it makes all the particles in the limit system jump. And so, in particular, particles in the limit system, due to the presence of this process, will not be independent, but we can show that this is the only source of common noise in this limiting dynamics, which means that particles in the limit system will be independent if we condition to knowing the value of this process. And so this is exactly what we called conditional propagation of chaos property. This we obtain if we believe that this is the limit system coming from the finite system that I presented before. We find that in the limit, particles are not independent, but they are conditional independent conditioned to this process. Okay. And even for the system, we can prove strong existence and uniqueness, so via standard techniques, Picard iteration and contraction arguments, as I've already showed you before, so I won't spend time on this well-posedness. And I want to present now our main result, so the convergence result. So this is our main result. And this statement tells you that if you assume that we initialize the system with independent and identically distributed initial conditions, and if you assume that B, psi, and F are bounded and Lipschitz and they satisfy the assumptions that I told you before, then for any n greater than 1, we can actually construct a strictly alpha stable process, which I will call Sn alpha. And we construct it on an extension of the original probability space where the finite particle lives. So in particular, on an extension of the space where the post-random measures are defined. We can construct it independent of the initial conditions and of these projected post-random measures bar by I. And we can construct it in such a way that if we consider the limit system that I showed you just in the last slide, driven by this strictly alpha stable process and by the same post-random measures I by I component-wise that you find in the finite, the same projected post-random measures I by I that you find in the finite system, and then we are able to control the distance between the positions at time t of two corresponding particles in the finite and in the limit system with the explicit convergence rates. So here the distances that we control are these distances that might be like strange looking. So some sort of cutted minimum between the L1 and L alpha minus distance in the case alpha less than 1, and this cutted L1 distance in the case alpha greater than 1. And this indicator function that appears in these distances is the indicator function to be before the first jump of the strictly stable process Sn alpha greater than k. And this alpha minus appearing here is any positive constant strictly less than alpha, the case alpha less than 1. And here, as I told you, we have explicit constants and we have ugly looking but explicit convergence rates in both cases. Okay, so just a few comments about this main result. So this actually states the convergence of the finite particle system to the limit system in a convenient and strange distance, which I will comment later. which is basically coming from the properties of the mu, the nearly stable law, and from the properties of the jump measure of the limit strictly alpha stable process. We have a strong convergence result, so a strong propagation of chaos. As Eva explained before, this means that we can construct the finite and the limit systems on the same probability space, and this allows to prove the convergence result via a coupling argument, and this in turn can yield explicit convergence rates. Okay, and again, this S alpha, which appears in the limit system and which we can construct for each n, is the so-called source of common noise. So it entails the fact that the property that our system has is the conditional propagation of chaos property. And as Eva explained before, in the weak rephrasing of this property, this means that the sequence of the empirical measures of the finite particle system converges in distribution to this mu bar t, so in this case to the conditional law of one coordinate on the limit system given the strictly stable process. So in the case of standard propagation of chaos, you have convergence to a deterministic measure. Here you have convergence to a random object, and this can be seen as a dynamical version of the law of large numbers. Okay, if we do just a little bit of more effort, you can also get rid of the indicator functions that you were seeing in our result, and you can actually prove that in the limit when the number of particles diverges, you can prove that you can control some appropriate Wasserstein distances between the marginal law at time t of two corresponding particles in the finite and the limit system. And so here again we have two different distances for the cases alpha less than 1 and alpha greater than 1. And in particular, this Wasserstein distance is a Wasserstein distance of order 1 defined with respect to this particular distance on R, so the one that you have seen appearing in our main result. And this in particular implies that we have weak convergence of finite time marginals of the finite system to the corresponding marginals of the limit ones. Okay, so now I would just like to give you an idea of the proof. So the main ingredient of the proof of this main result is we need to understand how the strictly stable process arises in the limit system. And that will be really the core of our proof. So I will focus on that part mostly. But we can say that the proof can be divided into 3 steps. So for any n, what we do is that we can find an approximation of the collateral jump term in the finite system in terms of a stochastic integral with respect to this strictly stable process. And this in turn provides us with an approximation of the finite particle system by means of some stochastic integral with respect to a strictly stable process. So this is the core part of the proof. And this is also the part of the proof where we actually construct this process as an alpha. Okay, then we need, and I will be clearer about this later, we need to approximate also the limit system. And then, of course, we need to control the distance between the approximation that we give for the finite system and the approximation that we give for the limit system. But this is basically Gromwell lemma. So I will speak in particular about these first 2 points. But you need to know that in all these steps of the proof, we will get some error terms and expressed in suitable norms, in different norms. And then we will collect all these error terms to obtain our final result. So I will speak about the first point here now. And before doing that, I need to tell you just a quick recap of basic properties of strictly alpha stable processes. And this will be all you need to know to follow the heuristic proof that I will give. So basic properties, first of all, as I already told you, S alpha, the strictly stable process, is a Levy process. So it has independent stationary increments and it has strictly stable increments. And this means that you can construct it by pasting together independent strictly stable increments. That will be what we will do in the proof. And then this also implies in particular that the process at time 1 is a strictly alpha stable random variable. So it has the properties that I showed you before. And also strictly alpha stable processes are self-similar, which means that the law of the process at time 1 rescaled by a factor t power 1 over alpha is the same of the law of the process at time t. And as I already told you, these are the key properties that we need in our proof, and this is the core of the proof. So just to give you an heuristic idea. So let us imagine we need to focus on this collateral jump term that I remind you. So imagine that we take the finite particle system, we fix any particle, for instance, particle I, and we look at its collateral jump term. And actually here I will denote it by A and T for short, but I'm also including in this sum the index j equal to I. So this is not exactly the collateral term that we have in a system, but the error that we make if we consider this extra sum and is negligible. So now we'll take this A and T. And now, as a first step, imagine that we fix and we keep constant all the jumping rates of all the particles. So imagine that on an interval 0t, we fix this function f, the jump rate, to be identically equal to some positive constant lambda for all the particles. So if we do this, then the total rate of the main jumps in the whole system during this interval 0t would be by a superposition n times lambda. And then the total number of main jumps of the whole system during this interval would be a Poisson random variable that I call Pn0t with a parameter that is given by total jump rate of the system during this interval times the length of the time interval during which I fix the rate. And this Poisson random variable will be also equal to the total number of summonds here. So to the total number of main jumps that one particle performs during this time interval. And so if you assume this, then you can rewrite by the basic properties of Poisson random measures, you can rewrite this A and T in this way. So as a random sum of IID terms distributed as nu, so nearly stable jumps in the domain of attraction of a strictly stable law, and they represent the collateral jumps that the fixed particle feels during this fixed interval. And this random sum will have a random number of summonds, which will be given by the total number of main jumps in the system during this interval. And then there will be this n power 1 over alpha factor coming from the normalization here. So now I will divide and multiply here by this Poisson random number of, by this Poisson number of main jumps, power 1 over alpha. So I will just do this. And now here you should recognize something that I showed you in the beginning. So this term here is a random sum of IID terms in the domain of attraction of a strictly stable law, properly renormalized with a proper rescaling, number of summonds, power 1 over alpha. And so this should remind you of what I called before a stable central limit theorem, except that before we had a deterministic number of summonds and a deterministic scaling. Here we have a random number of summonds. But if you believe that the stable central limit theorem still holds in this for this properly rescaled random sum, then what you get is that as n goes to plus infinity, this term here will converge distribution to a strictly alpha stable random variable that I call S alpha 1, so that the whole collateral jump term here, as n grows large, would be well approximated basically by the product of the strictly alpha stable random variable times a Poisson random variable power 1 over alpha times again the scaling coming from here. And now the next approximation that we do in our proof is that we replace these Poisson random variables by its expectation. So basically you use the law of large numbers for this Poisson random variable. So we replace it by n times lambda t. And so again, as n grows large, this collateral jump term will be well approximated by this product, where now n simplifies, and we take this t power 1 over alpha factor here, together with the strictly stable random variable. Here I call this variable S alpha 1 to remind you that it has the same distribution of a strictly stable process at time 1. So here we collect this factor and we recall the self-similarity property of strictly alpha stable random variables. So we write that this is equal in distribution to, of strictly stable processes. This is equal in distribution to the increment of a strictly alpha stable process at time t. And then we just rewrite formally this increment as an integral with respect to a strictly stable process. So if so far so good, if I didn't lost you, this should have convinced you of how this strictly stable process is obtained in the limit, basically out of the joint contribution of the collateral jumps, thanks to the stable central limit theorem and to the scaling that we have chosen for our finite particle system. Except that here you don't see the integral that we have in our limit system, but you see this integral, because of course we have this hypothesis, f is constant. And in a general case where f is non-constant, so in our case, what we do is that we discretize time. So we take our time interval 0t, we divide it into small time intervals all length delta, which will eventually depend on n, and we will go to 0 with n. And what we do is that on each interval, so for instance, interval k, we freeze the jump rates of the particle to the value that they have at the beginning of the time interval. So at time k delta, we keep it constant during the whole interval, so that within each small time interval, the total rate of the main jumps would be given by the sum of the rates of the individual particles at the initial time of the interval. And then, within each time intervals, we apply the approximations that we have seen above, so central limit theorem and law of large numbers, and we get that the total contribution of the collateral jump during any kth interval is given again, is well approximated again in the limit when n grows large by the product of a strictly alpha stable random variable, which is now relative to the interval k and comes from the central limit theorem, times total jump rate during this time interval times length of the time interval during which the rate is kept constant. And this is coming from a low large number as before. And now the total jump rate, as I told you, is this sum, is given by this sum, and we already collect this factor, and you can imagine what I will do in a moment. Now, we also want to sum over all the time intervals. So in the end, we sum over k, and we obtain that the total contribution of the collateral jumps during the whole interval, the big interval, is the sum over k of this quantity. So it's this quantity. And in particular, here I will rewrite this term with standard notation as the average of the function f with respect to the empirical measure of the finite particle system at time k delta. So I will write it like that. And here I will use the self-similarity property of strictly stable processes to say that this is equal in distribution to the increment of a strictly stable process over a time interval delta. And now you can guess that if I take delta to 0, then this sum would converge to the integral, the stochastic integral that we actually have in our limit system. And you can believe me if you believe that the sequence of empirical measures here converges to the conditional law on particle in the limit system, to mu bar, which is the meaning of conditional propagation occurs. So this is the heuristic, the main part of our proof. And just a couple of quick remarks. So yes, so basically this is what we do with interaction with the collateral jump term to discretize time. Just a comment, we can actually employ the stable central limit theorem within each time interval, and even if within each time interval we just have a random sum of nearly stable terms, and this is basically achieved using our previous result by two previous results, by Chen-Dunning-Su 2021 for the case alpha greater than 1, and by Chen-Dunning-Su, Yang and Zhang 2022 for alpha less than 1. And they provide in their papers a quantitative stable central limit theorem. So they quantify the convergence rate for this stable central limit theorem using particular Wasserstein distances. And what we do is that we basically generalize the results to a conditional setting, because in our case, we have random sum, and besides this, the number of summands is not Poisson in each time interval, but it is conditionally Poisson, given the information at the beginning of the time interval. So before using the law of large numbers, we also have to take into account this conditional distribution. And then I wanted to emphasize once again that you have seen that in our proof, on each time interval of length delta, out of the stable central limit theorem, we get the increment of a strictly alpha stable process over a time interval of length delta. We can perform a proof in such a way that these increments that we obtain in different intervals are independent. And these will be the increments, the strictly alpha stable independent increments that we will paste together to construct our limit process Sn alpha. Okay. So basically, all the error terms that you have seen appearing in our main result come from here. So from time discretization, stable central limit theorem, and law of large numbers, except for an extra contribution that comes from the need to approximate the conditional law of one coordinate in the limit. Oh, sorry, before I wanted to state this result. Sorry, I was forgetting about this. So this is the main result that we obtain regarding this representation of the finite system. So this tells you, again, this is basically the result that collects all the heuristics that I gave you. And it tells you that under the assumptions of the main result that I showed you before, so on B, psi, and F, and under IID assumptions for the initial conditions, for any n, and for a choice of delta depending on n small enough, we can construct this process on an extension of the space where the finite system lives and independent of the projected post-random measures. And with this process, we can give a representation of the collateral jump term in terms of a stochastic integral, stochastic stable integral. And if we make this approximation, we have an error, which I call RNT, which we can control in appropriate norms with explicit rates, in both cases alpha less than 1 and alpha greater than 1. So here we have a control on this error in this strange norm, like L1 minimum L alpha minus norm, in the case alpha less than 1. And here we control the L1 norm of the error in the case alpha greater than 1. Again, with the alpha minus, that is a positive constant strictly less than alpha. And so this is the representation of the collateral jump term that yields the representation of the finite system that we need. And these are all the error terms that I was speaking you about a moment ago. So this collects the error terms come from discretization, stable central limit theorem, and law of large numbers. And this is basically all the errors that we see in our main result before, except for another contribution that comes from the need to approximate the conditional law of one coordinate in the limit system by means of the empirical measure of the limit system. And you can guess that because you see that here in this representation result, we still have this empirical measure of the finite particle system appearing. So somehow we need to interpolate between a system where we still have the empirical measure of the finite system and the limit system. And so to do this, to approximate the limit system, we consider this new system, this auxiliary system, which is basically has the same equations of the limit system, except that here you see in the coefficients, you see the empirical measure of the limit system appearing, so mu and bar, defined as you can imagine. And if we take this system as an approximation of the limit 1, we make an error, which I call tilde R and T. And again, even in this case, we can control this error in both cases, alpha less than 1 and alpha greater than 1 via explicit rates. So again, we have a new result tells you that under the usual assumptions before, you can construct a strictly stable process and blah, blah, blah. And you can control this approximation error for the limit system with this some sort of a cutted L1 norm, in the case alpha less than 1. And you control this cutted L alpha plus norm for alpha greater than 1 with explicit errors. And again, these are constant explicit, these are error explicit, and these T and K appearing here, I remind you, is the first time where the strictly alpha stable process, the limit system, performs a jump greater than K. And this alpha plus here that appears in the case alpha greater than 1 is any constant strictly between alpha and 2. Okay, the proof of this result is basically based on a previous result by Fournier-Gulan in 2015. So they have a very famous paper where they take some probability measure on deterministic probability measure RD. They take n samples of this probability measure and they control the distance between the empirical measure related to these n samples and the target, the probability measure that they have taken. So we generalized the result, we adapted to, once again, to our conditional setting because we need to control the distance between the empirical measure of the limit system and a random measure, the conditional law of the limit system. But basically, it's just an adaptation of the result. And also, they quantify this distance in appropriate Wasserstein distances. And so this is what we also do. Okay. Just how much time do we have? We have 5 minutes.
Yeah, 5 to 10 minutes.
Okay, thank you. Then I will spend a couple of words about norms, which is my favorite part, and which allows me to connect again a bit with what Eva said actually, and mentioned and spoiled in the previous talk. So the choice of the norms that we used to quantify all these distances, approximations, errors, the choice of the norms was not immediate for us, and but is very interesting. And I will try to give you an idea of why you see these strange norms appearing. So for all the errors related to the collateral jump term to the finite system, so in particular in the first approximation result that I gave you for our collateral jump term, A and T, you have seen these norms. This is why I wanted to state it precisely. You have seen these norms appearing. So this sort of minimum between the L1 and L alpha minus norm in the case alpha less than 1 for some alpha minus strictly less than alpha, and the L1 norm for alpha greater than 1. And in the limit system, so in the last result that I showed you, approximation of the limit system, you have seen these norms appearing. So a truncated L1 norm for alpha less than 1 and a truncated L alpha plus norm for alpha greater than 1 with an alpha plus appearing strictly greater than alpha. And so the question is, why do we see all these, do we need all these strange norms? And the answer is that there is some difference in nature between the finite and the limit system. And now I will explain myself a bit better. So as I told you, recall that strictly stable random variables and nearly stable random variables and random variables in their domain of attraction have finite Q's moments only for Q strictly less than alpha. So this implies that the collateral jumps also have finite Q's moments only for Q strictly less than alpha. And this is why, when dealing with the finite particle system and with the collateral jump terms, we need to take, in the case alpha less than 1, Q equal to alpha minus, basically, and we choose to take Q equal to 1 in the case alpha greater than 1. So this is why you see these norms here. And instead, this limit process, a strictly stable limit process Sn alpha, as an associated jump measure, and in particular in the intensity of its jump measure, there is this new alpha appearing, which is the Levy measure of this strictly alpha stable process. If you don't know what is a Levy measure, don't care about that. The important part is that it has this form. And this means that every time for instance, you use Burkholder-Davies-Gund inequality on the limit system, you end up with integrals against this measure. And this means that, in particular, that small jumps of this process and big jumps of this process cannot be treated in the same norm, because big jumps larger than k for any fixed positive k have finite qth moment only for q strictly less than alpha, while small jumps of this limit process smaller than k for any fixed k has finite qth moments only for q strictly greater than alpha. And so what we do is that instead of using some transform function or a function to treat big jumps here, we throw away big jumps. So that is why you see this indicator function appearing. We put ourselves before the first big jump of the limit process, and we use this property of the small jumps of the limit process. So we use this finiteness of moments, which holds only for q strictly less than alpha. Sorry, strictly greater than alpha. So this is why you see in the results related to the limit system, you see this q equal to 1 appearing when alpha is less than 1, the L1 norm, truncated. And you see a truncated L alpha plus norm for alpha plus greater than alpha in the case alpha greater than 1. And then we take all these error terms expressed in different norms, and the way we put them all together to state our final result is by using the boundedness and Lipschitz properties of B, F, M psi. So this allows us to switch between one norm and the other, basically. And if I have 2 minutes, more minutes, also to connect with what Eva said in her talk, I would like to give just an overview of work in progress and future directions. So now I've shown you a strong convergence result, but our result is limited to finite time marginals of our systems. So we prove convergence in weak convergence of the law of time marginal law of one particle in the limits in the finite system to the marginal of the particle in the limit system. And what we are doing now is we are trying to prove weaker convergence results, so the convergence of the sequence of empirical measures of the finite particle system on the path space to this conditional law of one coordinate given the strictly stable process. And this is work in progress, well advanced work in progress. And then it would be nice to study the long time behavior of both the finite and the limit systems, but as Eva already said, this is already difficult in the case alpha equal to 2 when we just have a Brownian motion there. So this is future work. And then it would be nice also to study a spatially structured version of the model, maybe more realistic, where the interactions also depend on the positions of the particles that give or receive collateral jumps. And this is all. So I wanted to thank you, everybody, on behalf of both me and Eva, who's here with me. So if you want to appear, maybe I don't know whether you're appearing, but thank you. And this is a bit of literature. Sorry, there is also, okay, this is our work on which this talk was based. These are the works providing the stable quantitative version of the stable central limit theorem that I cited. And this is the work of Fournier-Gulan to control the distance between the empirical measure of the limit system and the conditional law one coordinate. And this is just general reference on strict alpha stable processes, which I found useful. Okay. Thank you.
Thank you very much, Elisa, for this very nice talk. I hope you can hear me. Okay, and are there questions? Let's see. As always, people just either you unmute yourself or you write in the chat. Maybe I start with one. When you do the time discretization, you said that, maybe you said it and I got lost. You need delta to be small enough. And it seemed to be some dependence on n as well, and I guess on alpha. Is there so do you have a dependence on alpha as well, or it's uniform?
No, this delta depends on n and should go to 0 with n, still keeping the total rate of main jumps, of course, non-zero. And it does not depend on alpha. We have some restriction on how small delta should be that are based on the norm of the supremum norm of f, but there is no dependence on alpha, no, just on n, no.
Okay, okay, interesting, thank you. I see one raised hand, so please, Leah, mute your side.
Hi, thank you for two really nice talks for both you and Eva. I was curious about this last comment about future work that you mentioned with extending it to the interactions depending on the particle position. How would, like, I guess the easier question is, how is this motivated by applications? But the harder question is, like, doesn't this ruin some of the exchangeability and other features? Like, what would be ways of trying to overcome that?
Well, regarding the first question, so it's motivated by application. As Eva told before, there might be different synaptic weights, so it does make sense to make these depends on distances. And regarding the second question, I think that it would destroy a lot of things. Like, for instance, as soon as we take nu to be centered, in the case alpha greater than 1, we have some Martingale properties that we can exploit. So we can work a lot with Burkholder-Davis-Conde inequalities. And if we introduce a non-trivial dependence on the positions, then I think a lot of things could be destroyed and a lot of things could be... I don't think it's easy.
But I think I can make a very short comment. Of course, it would not be exchangeable anymore. I mean, because you have these, but then you have to think that you have a lot of observations locally around some positions, and it would be a sort of multi-exchangeability, or I don't know how you would call that. There are these multi-population propagation of chaos results, no, where you have some subpopulations, and so it's a sort of. So I think
so it could depend on the positions, but like in a population-wise sense.
Yes.
You take dependencies in such a way to construct populations. Like in ground paper.
Yes, exactly.
Yeah.
Okay, thank you. That's an interesting. I didn't know about these other, like another way of thinking of locally having more particles then, and so in some sense you have fewer of these spatial distinct positions than you have particles, right?
Yes. Yeah.
Thank you.
Thank you. Are there other questions? So on this, maybe I have a follow-up question that, so thinking of dividing these into populations, and but you still have a sort of, Andrea, I saw your hand raised. I just asked this and then I give you the floor. So it's the, in my interpretation is always that somehow the graph of the interaction is a complete graph. And can you think of like just taking a graph, maybe when the average degree of interaction is still large, going to infinity, but it's a bit sparser, would it maybe do the same of thinking of a spatial structure?
That is also a good question. A difficult question. I think that as soon as the degree diverges with n, or like in a Milford setting, and that's fine. And we still have to take into account that to have the stable central limit theorem, we need some normalization with the size of the system. So I think that somehow, if you consider a non-complete graph, you should be able to get a stable central limit theorem. You should somehow be able to use that. So yes, maybe you can impose some conditions adding to the to be added to our to-do list.
Yeah. And for the sparse limits, I mean, we did not start to think about it. I mean, there are a lot of people working on that currently, but I think it's completely, it's really completely different. I mean, this the work of Kavita, Ramanan.
Yeah, exactly. Yeah, yeah.
We also have a look on that, but that is future work.
Yeah, it seems harder to track everything down. Yeah, thank you very much. Please, Andrei, you can unmute yourself.
Thank you. Thanks for the two nice talks. Question is about stochastic integral that you use. I think you mentioned stable stochastic integral. Is it conditional? I mean, by what is the usage based on the distance? And would you need any different stochastic integrals for the extensions that you mentioned at the end? Thanks.
Can you question? I had like going and I couldn't hear you well. Could you?
So, yeah, do you hear me?
Yes.
Yes.
You use, I think, stable stochastic integrals, so it is based. So, on what is this usage based on usage of your distance, and what kind of stochastic integral to use for extensions that were mentioned on your last slides? Thanks. Because I think it's one of the essences of the analysis, right?
Yes, of course. You're asking basically what we get in the limit in place of that stochastic integral if you start complicating your model. But I would say that as long as the stable central limit theorem holds, there must be some strictly stable stochastic integral. But in the
I think it will be some. Well, we didn't think about that in this stable.
maybe general Martingale
Yeah,
measure.
yes, general Martingale measures which have one component which is stable. Yeah. So we did that in the framework of the central limit theorem with the Brownian motion at the end, and then the specially version would be a Martingale measure, you know, because you have correlations that depend on the particle positions and things like that. So one underlying Brownian motion is not enough, so we need something like white noise there. But actually, we did not
think about
that for the moment. So we would also need something spatially extended than as limit, not only one-dimensional. Oh, it's a good question.
Thank you. May I still ask something? Let's see if no one else says anything. So you exclude alpha equal to 1, I guess, because it's some sort of a critical regime, right? Can you think of just using a different, like some log correction in your rescaling and still getting something? I'm not super familiar with this as a generalized central limit theorem.
I would say we're likely to get to that because the results were based on our work on points in that direction. So I would say yes, but still another bullet to add to our list.
But somehow that maybe you can take alpha equal to 1, just that maybe you rescale by something different and you expect to get the same, or is it behaving in a completely different way, this critical value, like the limit? Or
I have no idea because I haven't tried that.
I also don't know.
I would expect to be able to generalize these with much effort, but
we also need strong approximation results, which we didn't find in case alpha equal to 1. But
okay, okay, I see.
Was that excluded?
Yeah, alpha was excluded, but maybe in the last references that. So I'm pretty sure that there is something to be done for alpha equal 1.
Yeah, also because since you managed to deal with both of the other regimes, it seems weird that there's something going drastically wrong in that for alpha equal to 1. Yes, yeah, but that's super interesting. Yeah. Okay, let's see. Is there some other question? And I guess also in terms of stationary, like long time behavior, you can expect. I mean, if I've understood correctly, right? So far, you just have the convergence of the time marginal, but you know at least what to expect in terms of the full process, right?
Yes.
And so would also somehow, there should be also a way to tune the parameter to have some stationary measure, right?
Yeah, but as I mean, as in the previous talk, if you want to have a stationary solution of this limit, you need to include in the dynamic also this mu measure. So basically you think, okay, mu is, I mean, the law is stationary, so is also the conditional law, but it gives you, and then you have to solve this fixed point, but it is,
Yeah. And then maybe you don't even know if there's a unique solution.
but it's not finite
is a-
dimensional anymore. So
Yeah, but that's, yeah.
So maybe in some linear cases we should start with some cases like that where people are where you can solve explicitly things, but I don't know that in the diffusion case, but then well, it's not evident.
Yeah. Thank you. I think we have a comment in the chat.
Which is in homogenization theorems there. Oh wait, I can see. There is also special things to do when alpha is equal to 1.
I see.
So-
Okay, thanks. Yeah.
So might be not so trivial extension.
Yeah, makes sense. Yeah. Okay, so if there are no other questions, I think we can thank both of our speakers again.
Thank you.
Thank you for organizing.
Thank you for the very nice talks. And so